Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at some of the overview on computing strategies using Scikit-learn. Specifically, we'll look at how we can scale, how we can improve computational performance, and are there any ways we can parallelize the computation. So this is a very general overview of what's in the docs and not an in-depth insight. So let's get started. The very first option, if you are working with a big data, so if you have a lot of data, then there is something called as out of core learning, and that is generally used when the data is large, so large that it does not fit into the RAM of the computer. And in such instances, one of the options is to use uh, data streaming data as it comes in. So for example, if there is player data online that is coming constantly coming in from the uh, input sources, then that data could be read into the code by a different way, uh, which would use the streaming instances. So in scikit-learn docs, this is not discussed, but there are other libraries that work along with scikit-learn that uh, could be used for this type of method. The next one is extracting features. So if you remember in one of the previous videos, we looked at how we can vectorize a text document, and what happens in that case. For example, let's say there is a document that has three words. This is cat. In that case, the word this is and cat would become an individual feature in the feature column, and then each document would be checked if it has the word this. If it is there, then it will be flagged as 1, else it would be 0. And so uh, that is a memory intensive process. An alternative to that is extracting features using uh, this method, hashing. There are two functionalities that scikit-learn provides: feature hasher and hashing vectorizer. So for feature hasher, it can be used in this way. So let's say we have this document D is equal to we have this dictionary list of dictionaries, and in each dictionary we have a key value pair. So apple 88, orange 99, etc. And then the feature hasher can take that dictionary as an input and return this particular array down below. Here we can specify how many features we need in the output column, and according to that we get this matrix here. Because we requested 10 features, therefore we have 10 columns here, and there are two rows because we have two dictionaries. And so this is one way to get to convert strings to a feature vector or feature matrix as shown here. Another method is hashing vectorizer. It works in this way as shown here. Again, it uses the hashing trick. So each word, each string is then converted into a hash, and then it is assigned a particular index, and then that is converted to array right here. So again, here we have one, two, three, three strings, and we have three rows, and we have set the value of n features is equal to 6, and therefore we have 1, 2, 3, 4, 5, 6 features. So this is how hashing vectorizer works, and it can be used in either this, or this can be used in places where dictionary vectorizer or count vectorizer uses. So that is when the vocabulary, if it becomes too long, then it may not fit into the memory of the computer, and so this is an alternative to that. There are other incremental learning techniques, where if you have if the data set is too large, then you could pick chunks from that data, process it a small chunk at a time. And these are the methods that allow incremental learning. And we have looked through all of these in the previous videos, so definitely want to check them out if you haven't already. So for clustering, feature extraction, pre-processing, classification, and regression, in all cases, uh, there are some of the methods that do support incremental learning. And here is a plot from the docs which shows how increasing the training examples may help up to a certain point, but beyond that, the accuracy doesn't improve much as it plateaus out. Here we can see that the accuracy does improve up to 2500 data points, and after that it starts to plateau, and let's say around after 5000 or so it starts to plateau. uh, there is a wide fluctuation here. So that's another point to remember, is that if the data set is too large, uh, that does not necessarily mean that it's going to help improve the accuracy of a model substantially. Maybe so there would have to be a compromise between the speed that you need and the amount of data want to use for the training, because after a certain point the returns start to diminish. Another factor when working with large data sets is prediction latency. So if you have created a model and now that's in production, and if some user uses that model to get a prediction, then there should be as little prediction delay in prediction as much as possible. So faster predictions would be the best way to, like, it would be the best thing to have, but there are prediction latencies, and these are some of the issues that are listed here. One is number of features, input data representation, how it is represented, if it's a sparse matrix or dense matrix. There's model complexity and feature extraction. So for prediction purposes, according to the docs, the if you do predictions in bulk, then they are more efficient and they can be faster, as shown here on the plot on the right hand side. For the same models, here this is uh, bulk predictions, and here we can see that the prediction time max it's around 80 to 100 nanoseconds, whereas the left hand side it goes up to 6000 microseconds. Sorry, this is microseconds as well on the right hand side. Next is configuring for reduced validation overload. And the what this is to say is that if if the features are finite, you can check them well in advance and then specify sklearn underscore assume underscore finite. And so what that does is uh, the algorithm does not have to go through that step of ensuring that the features are finite, and that will save time as well. And below is the code to do so. Again, influence of number of features. We saw previously number of records. So if we go back, here we saw number of training examples. Now if you look at number of features, again, if you have more number of features, it could help improve the accuracy up to a certain point. But then no more number of features uh, uh, would also mean that the prediction latency it could increase. So that is to say that it will take a longer time to make the prediction. And so you might want to decide what prediction uh, accuracy is acceptable, and if that works for that particular case, then there's probably no need to go further and increase the number of features. So minimal features that give the required accuracy would be the best way to go. Input data representation is also something that could help reduce prediction latency. And the idea here is that if you have a matrix, a large matrix with a lot of zeros and very few values that are non-zero, then uh, processing all those main number of columns and rows would take more memory and more processing power. So to avoid that, that particular matrix could be converted into another representation which get rid of the zeros, and you have something like a CSR matrix, and so that representation would help speed up the process of prediction and reduce the prediction latency. And as a rule of thumb, according to the docs, the sparsity ratio is greater than 90%. Then, uh, then you could use these sparse formats uh, for converting the data, converting the good data to the model. And below is a function from the docs that shows how to get the sparsity. Next is model complexity. So the more complex a model is, the more time it's going to take for predictions. And here on the left hand side we have the plot which shows model complexity, non-zero coefficients. And as the model complexity increases, that is the number of non-zero coefficients increase, the prediction latency starts to increase as well. And that is another point to note, that the lesser complex model, if they give comparable accuracy, maybe that's the way to go. And according to docs here, we have increasing predictive power is usually interesting, but for many applications, it would be better not to increase the prediction latency. So we want to sacrifice prediction latency over higher accuracy. That's a decision that needs. Another point is feature extraction latency, and in this case, if what the plot is showing is that in the process of prediction, here feature extraction takes longer time than the rest of the part for the algorithm to run. And so if there is a way to uh, reduce this particular step of feature extraction, then it could help reduce the prediction latency and speed up the prediction process. And finally, here we have prediction throughput. So uh, uh, the suggestion here is that, as shown in the plot below, a linear model has a high throughput because they are relatively uh, less complex models, and so it has only 10 non-zero coefficients, whereas other models are much more complex. And to kind of increase the throughput, what this is suggesting is to spawn additional instances. So you have the same model, so you can have copies of the same model, and you can feed in input data separately to each of them. They may be running on different machines. Then you get like a parallelized approach to get the output of the predictions of the input data that you have. Then these are some of the final tips and tricks from the docs. One point that is made is, need to make sure that the NumPy is built using BLAS and LAPACK libraries. You can check that using the code that's written down. Then there is part of limiting the working memory. So uh, in this case, there is also a provision where you can specify how much working memory you want to dedicate to for running the code, and that is what is listed here. Next is model compression. So when inputting the model, so when you specify clf.fit, you can also write I dot sparsify. What that does is uh, it keeps the non-zero uh, non-zero numbers, and so it kind of compacts the matrix to help for faster processing. That's what this is about model compression. And before moving on, just want to mention that this particular step can yield 30% decrease in latency. So 30% speed up the process. Next is model reshaping. So model reshaping is uh, selecting only a portion of features to fit a model. So if you have 100 features, uh, instead of inputting all the features, if there are certain features that are very important, then only those could be included and rest of them could be deleted, or the rest of the features need not be used as an input to the model. And that could help that could help speed up the process of model training and prediction, because you now have lesser number of data that is being used for processing. And finally, there are two links that are provided if you need to read further in this. This is how to optimize speed, so using Python, C or C++. So there is elaborate documentation and starter code as well. So you could look into that, see if there are any other ways you can speed up the training process, reduce prediction latency. And if you are looking for different types of sparse matrices, then there is a link here, and there's CSR, CSE metrics that we have also discussed in this series previously. So the idea is that you convert the matrix in this format, and that would allow for faster processing. So that was it for this video. I hope this video gave you some intuition about how to leverage the methods within scikit-learn to speed up the process of training, speed up the process of prediction. If you have any comments or suggestions, please let me know in the comment section below. Hope to see you all in the next video. Until then, thank you.